Okay, this is the last lesson in the quantum model of light unit, and you should have a little bit of understanding of this just from doing the reading at the beginning of the class. And this is called the Compton effect. And the Compton effect came out of people who continued to kind of do research on into the photoelectric effect. So Einstein, he showed that photons had kinetic energy despite their lack of mass, which is kind of bizarre. And he then predicted that photons would also have momentum, although Einstein never proved this. It was a gentleman in 1923 named Arthur Compton who actually was able to, he performed an experiment that the results of which could only be explained by assuming that X-rays have momentum. And so then that, in that case, it proved Einstein's theory, and it convinced others that the photon model of light was actually valid. So again, we still have this wave model of light from the previous unit and from previous concepts and theories that has been proven, and now we've got this photon model of light that's also been proven, and that's leading us towards a new model of light. And so what Compton did was he shot high frequency and therefore high energy, right? Because remember that energy and frequency are related by that formula. He shot high frequency and high energy X-rays at a variety of materials, and that included graphite. And what he thought was that if light was a wave, okay, then this is what should have happened. Okay. He's got like a kind of incident X-rays that have a bigger wavelength. He's shooting them at graphite, and the X-rays that come through would have a smaller wavelength. That's what he thought should have happened if light was actually a wave. But what he actually observed happening was this. He shot incidents, there was incident X-rays that had a small wavelength, so higher energy, and they were shot at graphite, and X-rays with a longer wavelength came off at some sort of angle, okay, like that, but an electron was also ejected from the graphite. So although not the same as a photoelectric effect, a similar circumstance or similar result is a photoelectric effect. A wave of X-rays, like an X-ray photon knocked off, ejected an electron. So what Compton's observations were was they studied the way the electrons in the graphite scattered the X-rays. That could be explained by both the particle and wave models of light. Electrons were also thrown off the target, and the X-rays changed direction after the collision, and they had a larger wavelength. So that means they had a lower frequency than the incident rays, which meant they were losing energy. Right? So what we have happening is that the energy before of the photon ends up going into the energy after of the scattered X-ray as well as the electron. And the wave model of light couldn't predict this at all or explain it, nor could it describe the relationship between the angle that the X-rays and the electrons are coming off of and the wavelength. And so then this scattering of an X-ray by an electron is called Compton scattering. And so that's because, if we go back to this page here, what that means is that this wavelength is coming in here, and it's hitting an electron, and that collision that it's making with that electron causes an electron to be ejected, and then that electron also forces the X-ray to sort of be deflected from its original angle. What we have happening here is a collision, so we're leading to being able to talk about momentum, is what's really going on. That's called Compton scattering. The change in the wavelength of the scattered X-ray photon is called the Compton effect. So that difference in the wavelength between the incident X-ray and the scattered X-ray is called the Compton effect. And this interaction between X-ray photons and electrons, it has to obey both the law of conservation of energy and the law of conservation of momentum, because those are basic physics principles that cannot be broken. So what that means is that energy before equals energy after. And that energy before is energy of the incoming photon or incoming X-ray. And the energy after is the energy of the deflected X-ray plus the energy of that scattered electron. That electron goes off at an angle. Okay. And the formulas you would use for this are HF, and we could call that initial frequency if we wanted, is equal to HF final frequency plus 1/2 mv squared, where that mass is the mass of an electron, 9.11 times 10 to the negative 31 kilograms. And then the velocity is the speed of the scattered electron. In terms of momentum, and this is, the energy is physics principle number 5. Conservation of momentum is physics principle number 4. So momentum before equals momentum after. And the momentum before is the momentum of the incident, or incoming, I'll use the same language as I used above, incoming X-ray plus the momentum of the stationary electron in the graphite. That's before. And after, you have the momentum of the scattered X-ray, deflected X-ray, oh sorry, I'm trying to use the same language, deflected X-ray, plus the momentum of the electron. So the problem that we run into here is we know that the momentum of a particle is m times v, so mass of the electron, velocity of the electron. Right, in this case that's 0, but what in the world do we use for the momentum of a photon? Because we can't use mass times velocity because a photon has no mass and the velocity is always the same, 3.00 times 10 to the 8 meters per second. So something had to be done about that. Like this concept here is true. There's truth in this, so this is true. So somehow we need to be able to calculate the momentum of that incoming X-ray and the momentum of the deflected X-ray. And this is where Compton came in. And sorry, at the top here, I've summarized that. For particles, momentum is mass times velocity, but photons have no mass, and they always travel at the same speed. So Compton used Einstein's mass-energy equivalence, which says that E is equal to mc squared, to describe the mass equivalent. So he rearranged this formula to say that mass is energy over c squared. Okay. And then he used that then in the momentum formula. So momentum is mass times velocity, okay, which would give us energy over c squared, right, using this relationship for mass. And we would change that velocity to c as well, which then means that momentum would be energy over c. So if momentum is energy over c, so we have this here, I might run out of space, but we've got momentum is energy over the speed of light. This is on your formula sheet as energy is equal to momentum times the speed of light. And we know that energy is equal to h times f, or hc over lambda. Let's just put that in as a equals hc over lambda. So because we know that, then we can write momentum is hf over c, or if we put in for energy, momentum is equal to hc over lambda over c, then that just leads us to momentum is equal to Planck's constant over wavelength. Okay. And now we have a formula, two actually, that we can use. We've got a formula here that we can use to find the momentum of a photon if we know the energy, or if we know the wavelength, which of course then we can use to find the energy, we can find the momentum of that photon as well. And that photon is almost always an X-ray. So the momentum of an X-ray is P, and we find that by doing Planck's constant divided by lambda. So H is Planck's constant, F would be frequency in hertz, lambda's wavelength in meters, and the C that we use is always the speed of light. And Compton then also succeeded in showing that both energy and momentum are conserved in this interaction. So what we have for momentum before equals momentum after, and we have the momentum of the photon plus the momentum of the electron before equals momentum of the photon after plus momentum of the electron after. this then becomes h over lambda initial plus 0 equals h over lambda final plus mass times velocity. Okay, and we can use that to then calculate, to do collision questions with subatomic particles. And subatomic collisions are always elastic. So what that means is that the kinetic energy before equals the kinetic energy after. Always. And that kinetic energy is conserved. So we can do, we'll do a couple different examples here just based on that, and then we'll look at another relationship that evolved as a part of this. So we want to determine the momentum of a photon of wavelength 250 nanometers. So momentum is Planck's constant over wavelength, which is 6.63, always 6.63 times 10 to the negative 34 joules seconds. Do not use the electron volts version here. And then that's divided by 250 times 10 to the negative 9 meters. And that will give you a momentum of 2.65 times 10 to the negative 27. And the units here don't matter. You can put kilogram meters per second. Newton seconds for a photon is a little bit more appropriate because a photon does not have a mass. So using kilograms seems a little bit silly, although it's not necessarily incorrect. Okay, and the momentum of an electron, and we should know how to find the momentum of an object that has mass and velocity because that's going back to the first unit that we did in Physics 30. So 9.11 times 10 to the negative 31 kilograms because it's an electron and it's moving at 4 times 10 to the 5 meters per second. So we just multiply those out and we get 3.64 times 10 to the negative 25 kilogram meters per second. Calculate the momentum of an 8.5 kilo-electron volt photon. So energy here is 8.5 times 10 to the 3 electron volts. We need to get that in joules, so we're going to multiply it by 1.60 times 10 to the negative 19 joules per electron volt. And I'll do that when I put it into the formula. From the formula sheet, energy is momentum times the speed of light. So momentum is energy over the speed of light, which is 8.5 times 10 to the 3 electron volts times 1.60 times 10 to the negative 19 joules per electron volt divided by 3.00 times 10 to the 8 meters per second. And that will give you 4.5 times 10 to the negative 24 Newton seconds. Remember, you guys, you can stop and start this video as much as you need to catch up. I'm going through it a little bit fast just to be quicker about recording it, but you can stop and start as much as you need to. So now we kind of have this dilemma here because Young's double-slit experiment showed that light had the properties of a wave, and so that then led to the wave model of light. The photoelectric effect showed that light could behave like a particle in transferring its energy to electrons. Okay? And that seems to go back and support a particle model of light. Okay. And the Compton effect then furthered that. It also showed that light behaved like a particle, because only particles have momentum, and so if a photon has momentum, then really it's behaving like a particle. So this caused some consternation, and what it basically led to is what's called the wave-particle duality of light, or the wave-particle model. So any model of light must support this wave-particle duality. Okay? And the easiest way to think about it, or the way that I guess most physicists think about it, is that light travels like a wave. So light, or EMR, travels like a wave. But light, or EMR, interacts with other things as if it's a particle. So it interacts with matter. With more particle-like properties. And this actually, what this leads to eventually is what's basically called the quantum model of light. And that's just sort of a, that's a word that really means wave-particle duality, wave-particle model. The other thing Compton did was he also derived a formula that described the relationship between the change in the wavelength of the scattered photon and the angle that it moves at. And this is just purely like a formula to plug numbers into. It should be quite easy to use. Rearranging it algebraically might be a little bit difficult, but we've got change in wavelength is equal to Planck's constant divided by the mass of an electron times the speed of light times 1 minus the cosine of the angle that the X-ray scatters at. And what you want to remember is that change in wavelength actually means lambda f minus lambda I. Okay, so lambda final minus lambda initial. It's on your formula sheet, though, is change in wavelength. You need to remember final minus initial. And the mass is the mass of a scattered electron. It's 9.11 times 10 to the negative 31 kilograms, always. And c is equal to the speed of light, right? And then you've also got Planck's constant in there. And make sure you use Planck's constant in joules. So we'll do a couple examples here. We'll do one where we're solving for the wavelength of the scattered X-rays, and then we'll look at kind of doing some rearranging and maybe solving for the angle. So X-rays strike a metal plate, causing the ejection of electrons as shown in the diagram. I actually think this might be one from your workbook. It's just that I don't have a lot of examples for this, so I pulled one or two right out of your workbook. So, but that's okay. Try it again, even in your workbook, even if you write down the example, just to make sure that you can do the algebra on your own. So X-rays strike a metal plate, causing the ejection of electrons as shown in the diagram. Determine the wavelength of the scattered X-rays. So if we want the scattered X-rays, right? So this is lambda initial. Scattered X-rays is lambda final. That's what we're looking for. So lambda f minus lambda I equals h over mc times 1 minus cos theta. So lambda f is equal to 6.63 times 10 to the negative 34 joules seconds divided by 9.11 times 10 to the negative 31 kilograms times 3.00 times 10 to the 8 meters per second. And then all that's multiplied by 1 times cos of the angle. And remember, when you put that angle into your calculator, first of all, to be in degree mode, and second of all, to make sure you close that bracket, and then also close, like, so you're closing the first bracket around the end of cos, and then you're closing that second bracket, and then we need to add on that initial wavelength. 4.32 times 10 to the negative 11 meters. And that will give you a final wavelength of 4.34 times 10 to the negative 11 meters. Not a huge difference, right? It's a very subtle change in the length of that X-ray, the wavelength of that X-ray. It's also handy to be able to rearrange that formula, and this is a little bit more challenging to do. X-rays of 0.124 nanometers, so that's times 10 to the negative 9 meters, are incident on a metal foil. The scattered X-rays have a wavelength of 0.0129 nanometers, so times 10 to the negative 9. This is lambda f, this is lambda I. We want to determine the angle. Now, This is a really, this can be kind of a tough calculation. So I've not clearly left enough room on this board to be able to rearrange. So, well, I will rearrange, but we're going to have to squish it in a little bit here. So we've got, well, let's find change in wavelength first, because that'll, if we find the change in wavelength, we do final minus initial, that's going to just eliminate one variable that we have to have in that formula. So 10 to the negative 9 meters minus 0.0124 times 10 to the negative 9 meters. So that should give me, I need to grab my calculator. So that's 5 times 10 to the negative 13 meters. Okay, and that'll just help us a little bit. So then we have delta lambda is equal to h over mc times 1 minus cos theta. Okay. So let's plug some numbers in here and then maybe do some rearranging. 5 times 10 to the negative 13 meters is equal to 6.63 times 10 to the negative 34 joules seconds divided by 9.11 times 10 to the negative 31 kilograms times 3.00 times 10 to the 8 meters per second times 1 minus cos theta. So 1 minus cos theta is going to be equal to that 5 times 10 to the negative 13 divided by that whole expression. So 6.63, let's actually figure out what this is. Well, 5 times 10 to the negative 13 meters divided by, and I'm going to calculate 6.63 second e negative 34 divided by bracket 9.11 second e negative 31 times 3 second e 8 bracket. Okay, and that gives me 2.4259 times 10 to the negative 12. It's like joules seconds squared divided by kilogram meters, but we'll leave the units off of it for now. And so that equals that. So if I move over here, I end up with 1 minus cos theta is going to be equal to 5 times 10 to the negative 13 divided by that 2.4259 times 10 to the negative 12, which is 0.2061. So 1 minus 0.2061 is equal to cos theta. Theta is equal to inverse cos of 0.79389, which is 37.4 degrees. Okay, and that's a little bit more rigorous in terms of having to do the algebra, but it's doable. Especially when you recognize that h divided by mc is just always the same number. Like that number is always going to be the same no matter what it is. So then, in 1923, so like a little bit later with Compton, like just looking at symmetry in physics, because symmetry is a big thing in physics. So Compton had shown that waves could have momentum. You know, Einstein had shown that waves can, like a light can cause an interaction with, like light can hit a metal target and knock off an electron. Compton showed something very, very similar. So basically, what these things said was that waves behave like particles, and light behaves like a wave, and light behaves like a particle. So de Broglie actually wondered that if waves can act like particles, can particles act like waves? And so he suggested that since waves have a particle nature, then the opposite must be true. Particles must have a wave-like nature. So particles might have a wavelength, and they might behave like waves, which are called matter waves under appropriate circumstances. So momentum of a photon, the formula we had for that is that momentum is equal to h over lambda. And so what de Broglie did was he said that maybe we can use this to find the wavelength of particles. So lambda is equal to h over momentum, which then led to a formula for the wavelength of particles to be h over mass times velocity. So what that said was that particles could perhaps have wave-like properties if they were moving. Okay? So for an object to have a wavelength, a particle to have a wavelength, an object to have a wavelength, then it must be moving. And the thing here, though, is that matter waves of most objects have extremely short wavelengths that can't ever be measured. Only really small particles with longer wavelengths can show wave properties like interference and diffraction. And we're going to find out in the next unit, electrons do this. Okay? Electrons behave like waves under certain circumstances. And other subatomic particles do as well. So in order to observe wave properties, the slits in a diffraction grating need to be about the size of the wavelength, and that's really hard to do when you're talking about really, really tiny wavelengths. This is not something, you aren't responsible for knowing how to use these formulas here at all. This one, yes. These ones, this is an extension. It's not part of the curriculum. But I have seen it show up on a diploma exam, but they explain what's going on. They explain the formula to you, and they explain how to find the wavelength of an electron, and they'll give you this formula. It's not on your formula sheet, and then you might have to solve for that. In 1920, did I finish that? Yeah. In 1927, there were two guys, Davison and Germer. They actually did show that electrons diffract, and there can be an interference pattern when you use the appropriate material. And then they did prove that matter waves do exist. So particles have wave properties. So this wave-particle duality applies to objects, and it applies to light. Light behaves like a wave and a particle. Particles behave like a wave and a particle. And at the atomic level, at the really, really, really small level, you actually need both ideas in order to accurately model the world. And that's the photoelectric effect, or the Compton effect. And I'm going to talk a little bit tomorrow about the difference between the photoelectric effect and the Compton effect, because they're very similar, but yet they're different. Okay, and so that's coming up tomorrow. So in terms of the assignment, what you can work on in your workbook, a few questions. There's a lot of them are just in terms of the momentum of waves and stuff. There's not too many actual Compton effect ones with that big formula. But in your workbook, page 269 to 276, and you can also work on your unit assignment, because you now have everything you need to do for your unit assignment. Okay. And Michael, I have another copy of that if you didn't get my email that had the unit assignment on it. And the other thing I also want you to work on is that photoelectric effect graph question that I gave you on Friday. And again, I have some copies of that if you weren't here on Friday. I've left a few copies of that behind. And I'd like you to have that done for Wednesday, finished. And if you have it done now, you can hand it in. But I'd like you to have it done Wednesday, because part of our review on Wednesday for your exam on Thursday will be kind of peer reviewing that. So you guys will mark that each. Remind you again to be thinking about your egg curl devices. I'd like those to come in sometime this week. And if you have any questions about that, you can email me in terms of questions about that. But have a good day, you guys.